Today, we're talking about one of the most important ideas in modern AI. Seriously, it's the secret ingredient that lets these brilliant, massive models leave the research lab and actually work in the real world. On your phone, in your apps, it's a powerful shortcut called transfer learning, and it has changed absolutely everything.
I mean, think about it for a second. You see all this incredibly sophisticated AI everywhere, right? From photo editing apps that understand a picture's content to real-time language translation. We know that training these giant models can take weeks, even months, on huge clusters of super powerful computers. So how in the world does all that power end up in your pocket?
Well, the answer is they cheat. Kinda. They don't start from scratch every single time. That would be completely impossible. Instead, developers use this really clever, really elegant shortcut that saves an unbelievable amount of time, money, and data.
So in this explainer, we're going to pull back the curtain on this exact technique. We'll break down how AI essentially learns to stand on the shoulders of giants, making it possible to build amazing things faster, cheaper, and way more powerfully than ever before.
Okay, so first we have to really get our heads around the problem this shortcut was designed to solve. And it is a problem of absolutely mind-boggling scale. To teach an AI model from a totally blank slate, you need an amount of data that is just almost unimaginable.
Just look at this number for a second. 3.3 billion. To get a foundational language model like BERT up and running, it had to chew through 3.3 billion words. That's not a few books. That's like reading a huge chunk of the entire internet. Now imagine having to do that for every single new AI feature. It would be completely unsustainable. No one could afford to do it.
And here's the why behind that huge number. Without this colossal flood of data, a model can't learn the absolute basic building blocks of its world. It wouldn't know what edges and textures look like in a picture, or what grammar and context even mean in a sentence. It would be like trying to understand physics without ever seeing an apple fall. You just have a bunch of random facts with no underlying principles.
So if starting from scratch is the problem, what's the solution? This is where our hero arrives on the scene. Let's finally meet the concept that really did change everything: transfer learning. The core idea is actually super intuitive. You just take a massive model that has already learned all those general features from a huge data set, a model that's already seen millions of images on ImageNet, and you simply reuse that knowledge. We're not teaching the AI how to see from scratch, we're just teaching it what new things to look for, like spotting anomalies in medical x-rays. It already gets the basics, like edges, shapes, and textures.
Now, there are two main ways people apply this shortcut. The first is called feature extraction. This is kind of like taking a powerful pre-built engine out of a sports car and just locking it down. You don't touch the engine itself, you just build a new custom chassis around it for your specific task. It's fast and it's stable. The other method is fine-tuning. Here, you take that same engine, but you gently tweak and tune all of its parts to squeeze out every last bit of performance for your specific race. It's definitely more powerful, but as you can imagine, it requires a lot more care.
So how do you choose which one to use? Well, it all comes down to a few key trade-offs. If your own dataset is really small, or your new task is super different from the original one, or you just don't have a ton of computing power, feature extraction is your safest bet. It stops the model from getting confused and messing up its core knowledge. But if you've got a decent amount of data, your task is pretty similar to the original, and you have the horsepower, then fine-tuning is almost always going to give you better results.
All right, so transfer learning is powerful, but it's not magic. It's not a silver bullet. What happens when the world your model was trained on looks totally different from the world it has to actually work in? This is the huge, critical problem of domain shift.
And domain shift usually comes in two main flavors. First, you have covariate shift. That's when your inputs change, but the basic rules stay the same. Think of a product recommendation model trained on teenagers that now has to work for senior citizens. The who changed. But the trickier one is concept drift. This is when the rules of the game themselves change. For example, a model built to predict if someone will default on a loan is going to completely fail during a recession because the very features that define a risky person have fundamentally changed. The why changed. So how do we fight this? Well, one of the most clever solutions is called Domain Adversarial Training, or DAN. It basically works by having the model play a game against itself. One part of the model, the task head, tries to do its job, like analyzing sentiment. But another part, the domain head, acts like a detective, trying to guess if the data it's seeing comes from the original training set or the new one. And the genius move is in step 4. The model is trained to actively fool the detective.
By learning to create features that the detective can't place, it ends up learning features that are so general that they work equally well in both worlds. It's brilliant.
Okay, so if we take these ideas to their logical extreme, we end up right on the cutting edge of AI research. What if a model could learn a brand new task, not from thousands or even hundreds of examples, but from just a handful? Or what if it could learn from none at all?
This brings us to few-shot learning. It's the ability to generalize from an incredibly tiny sample size. This is much closer to how we learn. If I show you just 1 or 2 pictures of a weird animal called a quokka, you'll probably be able to recognize any other quokka you see for the rest of your life. AI is finally getting that same ability.
But what if we go even one step further? This is where it starts to feel like actual magic. With zero-shot learning, a model can correctly identify something it has never seen an image of before, based only on a text description. It could, for instance, correctly identify a picture of a tiger without ever being shown a single photo of one in its training.
So, how on earth is that possible? Well, it's all about creating a shared mathematical language, a kind of conceptual space. Models like CLIP learn to map both images and text into the same space. An image of a tiger gets turned into a specific set of numbers. The description, a large carnivorous feline, also gets turned into a set of numbers. And the model's only job is to figure out which image's numbers are the closest match to the text's numbers. It's like a universal translator between what we see and what we say. Now, as powerful and as magical as these shortcuts sound, they are not foolproof, not at all. And if you use them carelessly, you can actually make your model worse than if you had started from scratch. So it is absolutely critical to understand the common ways they can fail.
The first big pitfall is something with the dramatic name catastrophic forgetting, and it's as bad as it sounds. This is when you fine-tune a model on your new task, and in the process, it completely overwrites and forgets all that amazing knowledge it had from its original training. It's like cramming for a history exam and then walking out and suddenly forgetting how to do basic math. The new knowledge just completely wiped out the old.
And then there's the second one, negative transfer. This is pretty much the ultimate failure mode. It's where you take the shortcut of using a pre-trained model, and you end up with worse results than if you had just trained a small model from scratch on your own data. This usually happens when the original world the model learned from and your new world are just too different. The old knowledge isn't just unhelpful, it's actively harmful.
So how do we avoid these disasters? Well, it mostly comes down to being careful and following a practical checklist. When you're fine-tuning a big model like BERT, these are the rules of thumb. But I want you to pay very close attention to that one with the warning sign, because it's the mistake that trips up everyone, even experienced pros. The learning rate. Using a standard, high learning rate is like turning a fire hose on a delicate sand castle. It just obliterates all that intricate pre-trained knowledge. You have to use a tiny learning rate to gently nudge the model in the right direction.
And that kind of brings us to our final thought here. We started this whole journey by explaining how transfer learning lets AI work on our phones. But we've ended up in this wild new world of few-shot and even zero-shot learning. So when AI no longer needs these massive data sets for every single new problem, what becomes possible? What scientific discoveries or medical diagnoses or creative challenges that were just completely blocked by lack of data can we finally start to solve?